Previously, we identified that something like a mutex is not super amenable to our model of single ownership because we need multiple threads to have access to this mutex. And nothing that we saw really so far would get the job done. If we are going to clone it, well, that wouldn't work because clone would create a copy, and the copy would also copy what's inside of it, so we would be looking at two integers protected by their own mutexes. That wouldn't make the code work the way that we need it to work. And similarly, we can't just throw around references to the mutex because that's not adequate for ownership and mutability and what have you either. So what do we do? Well, we have to break the single ownership rule. I know, insert scream emoji here. And this requires a little more background, actually, on smart pointers and reference counting. Okay, you know about pointers, I imagine, having previously programmed in C and or C++. And if you've done more modern stuff in C++, you may also have seen smart pointers. And smart pointers exist in both C++ and Rust, and we're going to talk about two different kinds in this topic, the box and the reference counting type. The idea of the smart pointer is, as I say, not unique to Rust. What's different about this, what makes it valuable, what helps make Rust rely on this and produce code with hopefully fewer errors, is the strict enforcement of the rules around smart pointers, as we'll see. Okay, so we'll start with the box. The box we're just going to brush past very quickly in what we're doing here. Box is a generic, and you can put a type in it, and it's an easy way to put some data on the heap rather than on the stack. This is good for a situation where you want to take some input from a user and you don't know in advance how big it's going to be, or when you want to transfer ownership of some data, move it around from one thread to another, but you want to do so as a move rather than a copy. Then you create a box using its new function, and as expected, it's heap allocated, and you get the behavior that you would normally get for heap allocated objects in Rust, in that we have ownership and it gets dropped if the owner goes out of scope. But that is pretty simple. What we're interested in talking about mostly is the reference counting. And reference counting is a reference-counted smart pointer, and it allows for shared ownership, counting, of course, including this nice picture of the count, and this value that we are holding on to with our reference-counted pointer only goes away when the last reference to it is dropped. You may have learned about reference counting in a different context. If you learned previously about, say, garbage collection, an earlier version of garbage collection relied on reference counting, for example, and so if there were no more references to a particular piece of memory, then you could say, all right, well, it's gone out of scope and it can go away. And there is something to this effect here, in that we have references to some memory, and if there's no more references, well, then we can get rid of it. However, in Java, anything can be a reference. Assign A equals B, and you've created a reference. In Rust, we have to be explicit when we want to create a reference-counted object, and use the type RC, and it's generic, so it takes a type parameter, so you can have reference count of widget, and that would get the job done. So to make that, you instantiate that type to get an object, and if you want to make another reference to that same object, use clone. And clone increases the reference count, and so if you want to hand this over somewhere, you, clone, and you hand over the copy, and now there are two references to this thing. When a reference goes out of scope, it leaves from a function, you don't need it anymore, then the count decreases, and this continues until eventually the reference count, hopefully, gets to 0, at which point, then, the last reference having been dropped, the object inside of it can go away and will be dropped as well. It's important to note that reference types can leak memory. If you have a cycle in your references, then the memory will never be dropped. It is, of course, undesirable because your reference count can never get to 0 because there is a cycle keeping all of these things alive. That is potentially a form of memory leak, and this is something that would be a problem. So broadly, you want to avoid using reference counts unless you are certain that you won't end up in this cycle kind of situation. And it is noteworthy that unlike the C++ analogous shared pointer, you can't keep a reference to the internal value after the reference counted type goes out of scope. That's because the value is owned by the pointer and is definitely freed when that pointer goes away. In the same way that the mutex contains the type that it's protecting, the reference count contains whatever you've put in there, and you can't access it without going through the mechanism of the reference counted object, and you can't access things in mutex without going through the mutex approach. Okay, so we've got an idea. We have reference counting. Well, do we have what we need to pass the mutex around? Not quite. The RC will not work when we try to pass it between threads. Well, why not? So the management of its internal counter is not done in a thread-safe way. This is something that documentation will tell you if you're curious to take a look. And so this means it can't be sent between threads safely. As we will have seen in the previous topic, that means it does not implement the send trait, and it's a way of suggesting to you, if you try to use an RC and pass it between one thread and another, that actually what you want to do is not cool because the thing that you are operating on, the reference counted type, is not thread safe. If we want that, there is, as I said also last time, no way to implement the send trait and just say, yeah, I'm sure it's fine, carry on. What we actually need is a different type. And the different type is the atomic reference count, ARC, or ARC. And it is perhaps slightly slower than the regular reference counted type, but it is exactly what we need here. If you're not passing data between threads, you wouldn't use the atomic one because, again, potentially slower. But if the goal is to pass data between threads, then yes, definitely you need to use this, and the compiler will stop you if you try to use the wrong one. So here's a quick example of a little program where I wanted to catch a SIGINT using an atomic type. The program in question, where the do things comment exists, was actually about receiving incoming connections and then sending back a response. So it was a little network program, not super exciting in that regard, unless you really are into socket programming. But this, for the purposes of the example, was a good way to actually work with setting up a Control-C handler. Okay. So I have to import the correct type. It's in the sync package, so ARC for atomic reference counting, and I also have some atomic types in there as well. We'll come back to the subject of atomics in some more detail a little bit later on. But I use a mutex to protect a Boolean that's used concurrently, even though it's not in two different threads. The interrupt handler, in this case, which is catching a SIGINT, a Control-C, does not necessarily run a different thread. However, it's asynchronous, so it can run at any time, and you can get race conditions caused by a signal handler, if you remember that from an earlier concurrency course. Okay, so what I'm going to do is create the quit mutex, and it is a mutex around a Boolean variable, which is false. And then I'm going to clone it, and I'm going to name the one that goes into the handler quit. You do have to clone the atomic reference counted type when you're passing it around, otherwise you would just move the only one copy that you have. So we do need this let handler quit statement to exist. And so when you are passing a mutex between threads, you will clone the mutex each time when you are creating the thread so you can pass it in, and then that thread has it. Sounds good. You do the same if you were doing it with message passing. If you wanted to send the message to another thread saying, here you go, here's your mutex, which you could. Mutex by mail is valid. You would have to clone it, otherwise the first time you send it, oh no, we no longer have possession of the mutex and it's gone now, we can't clone it again. Okay, Then I'm going to set the Control-C handler, which is, again, catching this SIGINT. And we're going to set the handler. We're going to move, because it, like a thread, takes a closure. And what we'll do is unlock the mutex, unwrap, and we will assign B is true. At the end of the execution of the handler, of course, the mutex guard is dropped. And otherwise, that's the end of the invocation. And we also have an expect for setting up the handler. If something goes wrong in setting it up, tell me about it. Sounds good. That makes sense. And then in the actual event loop for the program, while quit, while we lock, unwrap, so get the value as long as quit is false, because there is a negation on that condition, do things. As I said, the things that we are going to do are, in this particular program socket example, which is not relevant at this point. We just wanted to show how to create the handler, pass the mutex into a different context using the atomic reference counted type. We should still remember, by the way, there exists a possibility of a deadlock in Rust, even if the mutex is automatically unlocked for us. Nothing really prevents thread 1 from acquiring mutex A and then B, and then thread 2 from concurrently acquiring B then A, and you end up in that scenario with each thread waiting for the other, and you have a deadlock. The language cannot solve all concurrency problems. That would be nice, but is somewhat unrealistic. So you should keep in mind that it's good at solving some of the problems that we might encounter. All right, so let's talk also about lifetimes. And lifetimes, in the words of Roy Batty, I want more life, Father. Very good movie if you haven't seen it. Not for everybody, I suppose. Many of my friends don't like it, but they're allowed, I suppose, to have their own opinions, even if I don't agree. So we've said that the compiler makes a determination about how long a piece of data will live. The system is not perfect, and sometimes we have to help it a little bit. As Rust gets further development in terms of how its compiler works, you will probably have to do this less and less and less. The number of times you will have to do this in the course is hopefully not a very large number, and certainly in a couple of years after some more development has gone on Rust, you will probably find that some of those things will no longer be necessary because the compiler will be able to work it out for you. But sometimes we have to help it a little bit with lifetimes. So here's a simple program in the official docs that doesn't compile because the system isn't sure what is correct. So we're going to create a couple of strings. String 1 and string 2 are a string from ABCD and XYZ. And we're going to call the longest function. The longest function takes both strings as references to the underlying string representation. Fine. And if X length is bigger than Y length, it returns X. Otherwise, it returns Y. And the thing is that we're not entirely sure how long strings are going to live. The compiler can't figure out whether the return value of this function, at least right now, is a borrowing of X or Y, so it doesn't know how long X or Y has to live for things to work out, for us to be sure that all the borrowing guarantees are upheld. You might think, actually, that's kind of silly. You might think that's really obvious. You can look at that and you can say, well, listen, I know that X and Y are really string 1 and string 2, and they totally live long enough for the print line macro, and really there's no problem there. Thing is, the compiler makes decisions based on local information. And that local information is just what is the content of this function. So when it's deciding how to compile the longest function, it only looks in that function, and it treats longest as if it could take any two string references that come from anywhere. Now, there's no specific restriction on which references it could be. We know by doing full program analysis, ourselves, manually looking at it with our eyes, we can see that, all right, we know that longest is only called in one place and only with two particular arguments, and therefore there's really no concern. But the compiler doesn't do that. And honestly, this is just a very simple example to show what happens when we don't know at compile time. If the compiler were clever enough to solve this, I would give you a more convoluted example that shows you the same behavior where you have to help it with the lifetimes. It would just be perhaps a little harder to fit on a slide. So, knowing that it takes longest as if it could take any two string references, what do we do about that? Well, we annotate. We specify the lifetimes. And the thing about annotations is they don't change how long references live, really. The memory is still dropped at the same point where it would have been otherwise. It just describes the relationships between lifetimes of references. And so you put it on functions to say what you will accept and what you can return, but again, it doesn't change anything about what actually happens with the references. It just says these are the minimum standards that I'm okay with. If you want an analogy on this, think of it as saying something like, I'm going shopping and I want to buy eggs, and I will only buy eggs that have an expiration date that is at least 2 weeks in the future. So 2 weeks from today. If I go shopping with that rule, it does not change any of the eggs that are in the store. Whatever expiry dates they have, they had them before I even decided to go shopping, and they will have them no matter what I buy or don't buy. It does not mean that eggs that have an expiration date that is sooner than that, say next week, are poison and nobody should eat them. It does not mean I will accept only eggs that have an expiration that is exactly 2 weeks in the future. I will happily buy them if they have an expiration date in a month. I'm just setting a minimum standard, and I'm saying this is what I want, and I will not accept anything that is less than that standard. And as long as it is at least that long, we're fine. If it's not, then I won't buy it. I won't accept it. Not okay. So hopefully that gives you some idea. And lifetime annotations are usually written with an apostrophe followed by a name, and they appear in angle brackets. The names are typically really short, like apostrophe A or apostrophe B. And so what you are saying here when you are specifying is you're saying, okay, this function here, longest, it must exist in lifetime. It takes parameters and responses in lifetime A. X has to have a lifetime of A, Y has to have a lifetime of A, and the return value will be also having a lifetime of A. And this does what we need. The first annotation in this line, the one after the name of the function, says that all parameters and the return value must have the same lifetime, and then we are specifying we will accept strings and string references that live at least as long as a designated lifetime. That is, it has to live at least as long as the shorter of the two, X and Y. The actual lifetime isn't that important as long as we're following the rules of being at least that long. In early versions of Rust, lifetime annotations really had to be specified everywhere, and that was kind of annoying. Fortunately, the compiler can now identify a lot of common scenarios, so it is unlikely that you will have to write a lot of lifetime annotations, but if you do, now you know what is there. The borrow checker can put them in where it needs them, and if you see some previous Rust code, you might have seen it already, or if you were digging through some example on Stack Overflow or something, you might see annotations, and they don't do any harm as long as they're correct, but if they're not needed, you don't have to put them, so just be aware of that. Now wait a minute. I said at the start of this lecture that we were going to break some rules. We're not breaking rules, we're applying more rules. That's the opposite of what we want. No, the rule-breaking thing is the ability to grant a particular piece of memory immortality. Or, in the words of then Chancellor Palpatine, the dark side of the Force is a pathway to many abilities some consider to be unnatural. And the obvious question that you have, as you must, is it possible to learn this power? And the answer is yes. If you specify a lifetime for a particular piece of memory as a special one, which is static, you grant the ability for this memory to live for the entire duration of the program. You should keep in mind that just because it can doesn't mean it necessarily will live forever, only that it could. This can be used correctly to tell the compiler that a particular reference will always be valid, such as string literals that are always going to hang around. You have defined somewhere some responses, invalid input, incorrect parameter, something like that. They'll always be valid. They'll always hang around. You can say they're static, and the compiler will consider them to be immortal. Not too bad. It's also used in a couple of cases, and one of them is in the interface for spawning a thread, which happens because you can pass anything to a thread, so the compiler wants to be sure that whatever you're providing is definitely going to live long enough for the thread, which can live an arbitrarily long life. Threads are estimated to be immortal. I mean, they can exit, but they don't have to, so the compiler, assuming always worst-case scenario, will say, well, what if it does live forever? But for the record, the kind of immortality that I'm talking about is the Lord of the Rings elves kind of immortality, which is that they don't die of old age or natural causes or anything like that, but they can die in violence or grief. So this can happen with your memory as well. Threads can exit, threads can be canceled. Cancellation is a little bit like murder. And static variables can be dropped if the compiler is sure that it's safe to do so. However, there is a possibility that they could hang around indefinitely. And for that reason, we consider them to be immortal, but in the sense of Lord of the Rings or The Hobbit kind of immortality for elves, not actual, like, invincibility kind of immortality. Now, I said don't do this earlier, and sometimes when you're trying to pass an argument to a function or something like that, the compiler will say, well, the lifetime of this is not enough. I suggest making it static. No, don't do this. It's a bad idea. Convenient as it is, should the compiler actually suggest it, you think, all right, yeah, I will apply that suggestion. Don't. Just don't. We don't do that here. You should apply the correct lifetime annotations or fix what would be a dangling reference, because that's usually what's kind of happening. The compiler is unfortunately leading you a little bit down the wrong path when it says, listen, I want this vector that you're trying to pass to a thread to be annotated as static. Okay, so you say, all right, I'm going to annotate the function parameter with this lifetime, and that just moves the pane up a place in the call stack to where the function is called. So you modify those, and you would just keep doing that over and over again. So like, okay, function foo, which takes this parameter, it has to have the annotation of static for that vector, and then it happens in bar, and so on and so on. And before you know it, you're back in main, and you're saying, well, how do I make a vector have a static lifetime? That's kind of the wrong thinking, and you can waste some time, and I'm not too proud to admit I wasted some time going down that road on a couple of little programs that I wrote. What the compiler actually means when it's telling you, I think that this needs to be static, is that a reference is not appropriate. We need to either move the data, copy it, and then move the copy, or use another construct like the atomic reference count that is appropriate to that situation. So if you see you're trying to provide something and the compiler says, I don't think so, it should be static, don't do that. Don't just slap static on something because you will just waste your time. Use the correct construct. Probably you need something like atomic reference count. And this one is philosophical as much as anything. It is just keep in mind that making something immortal isn't always a win. Memory that's kept around forever but is no longer useful for any reason is fundamentally very much like a memory leak. That memory is in use and it can't be reclaimed by the operating system. It can't be put into anything else. It doesn't do anything if you don't need it anymore. So keeping it around forever, even though it might be possible to deallocate it in some hypothetical sense, is not good either. So just making everything static to avoid the possibility of having to think about lifetimes, or to avoid any risk of needing to annotate things, anything like that, is not a good solution. It's wasting memory that you shouldn't waste, and that is ultimately a little bit detrimental to performance. So use static if you must. It should not be your first choice in terms of working with memory and lifetimes.